shall start module. Okay, so I shall start module 2, which is Introduction to Deep Learning. So though I introduced deep learning to you during the first module, again, we will see briefly that what exactly the deep learning is. And these are the major contents of this unit. Deep learning and its architectures, activation functions, and hyperparameter tuning, which we already discussed during module 1. Supervised and unsupervised deep learning. So this topic I'll cover with the first topic only, that is deep learning and its architectures. And otherwise, the supervised and unsupervised concepts are same as we discussed in machine learning. And the last one is improving deep neural network bias versus variance trade-off, which was not discussed. So I'll discuss bias versus variance trade-off, discriminative analysis, batch normalization. So all these topics are not discussed. So mainly in this unit, I will discuss the first and last because they are left, and the second and third, they have already been discussed. Okay, so let us start with the introduction of deep learning, though you have already studied that what exactly the deep learning is. I'll quickly tell you the differences and similarities between deep learning and like other concepts. So machine learning, as we know, is a collection of algorithms and tools that help machines understand patterns within data and use and this machine learning algorithms use this underlying data structure to perform reasoning about a given task. And as you can see in this figure, this machine learning is a subdomain of artificial intelligence. There are several subdomains of artificial intelligence, as we discussed earlier: machine learning, natural language processing, then expert system, fuzzy logic, neural networks. All these are major subdomains of artificial intelligence. And among them, machine learning is one of them. Okay. So this machine learning, machine learning algorithms, for machine, there are many ways that machines aim to understand the underlying patterns in data. But how does machine learning relate to deep learning? That I'll tell you. There is a growing misconception that deep learning is competitive technology to machine learning domain. No, deep learning is not a competitive technology to machine learning. It is in fact subdomain, as you can see in this figure. So deep learning is a subdomain of machine learning, which accelerated computational power and large data sets. And deep learning algorithms are able to self-learn hidden patterns within data to make predictions. So it is like they deep learning algorithms, they also do the task similar to machine learning, but usually here we use big data. You can think of deep learning as a branch of machine learning that is trained on large amounts of data. And this deep learning algorithms, they deal with many computational units working in tandem to perform predictions. So major one of the differences is this deep learning algorithms, they work with a large amounts of data. Okay, and now let me tell you then what is the similarity between deep learning and human brain. Okay, so deep learning and human brain, they are they perform similar jobs in an effort to create systems that learn similar to how human learn. How human learns. The underlying architecture for deep learning was inspired by the structure of human brain. For this reason, quite a few fundamental terminologies within deep learning can be mapped back to neurology. And similar to how neurons form the fundamental building blocks of our brain, this deep learning architecture contains a computational unit that allows modeling of nonlinear functions that is called perceptron. Okay, so the magic of deep learning starts with the perceptron, we can say. If you remember, we discussed that perceptron is one neuron. So the magic of deep learning starts with the perceptron. Similar to how a neuron in our brain transmits electrical pulses throughout our nervous system, the perceptron receives a list of input signals and perceptron transforms them into output signals. So remember that perceptron is one neuron. So it receives a list of input signals and it transforms them into output signals. So this is like similar to what neuron does in our brain. Perceptron aims to understand data representation by stacking together many layers, where each layer is responsible for understanding some part of the input. So this is like here I am talking about the hidden layer. So layer can be thought of as a collection of computational units. That computational unit means, again, I am talking about the perceptrons, multiple perceptrons, or you can say multiple neurons. So a layer can be thought of as a collection of computational units that learn to detect repeating occurrence of values. And each layer of perceptrons is responsible for interpreting a specific pattern within data. So network of this perceptron mimics how neurons in the brain form a network. So the architecture is called neural network. So which we already learned during the first unit. So now I am not discussing about the artificial network because we already learned about the artificial neural network. So I'll not learn, I'll not discuss about the artificial neural network again. Fine. Okay, so now let us see what exactly, because then from this concept of biological neural network and this concept of brain, artificial neural network, they came into picture many years back. And now we are talking about the deep neural network. So let's see then how what is deep neural network and how they differ from artificial neural network. So deep neural network is simply a shallow network with more than one hidden layer. With if you remember, we discussed that artificial neural network may have one or two hidden layers, and that is called like shallow neural network. Deep neural network is also shallow neural network having more than one hidden layer, maybe two, three, four, five. Right. So, like, these are not many layers, but these are some layers, like more than one. So, deep neural network is also a shallow neural network. Each neuron in the hidden layer is connected to many other layers in the network, and each arrow has a weight property attached to it, which controls how much that neurons activation affects the others attached to it. So that we already discussed. Okay. Okay. The word deep in deep learning is attributed to this deep hidden layers. Okay. We can have deep hidden layers. So what does it mean? Deep hidden layers, and it derives its effectiveness like when we have many layers. Okay, so selecting the number of hidden layers for deep neural network, it depends on the nature of the problem and the size of the input data. Please remember this. Okay, selecting the number of hidden layers depends on the nature of input data and the size of input data. And the figure on the right side shows a deep neural network with only two hidden layers, right? That is okay if the problem is simple and the size of data is also reasonable. If it is not big data, then this deep neural network, which I have shown on this slide, can be used. It has only two hidden layers, but then too it can be considered as deep neural network because more than one hidden layer is there. Okay. So that is like deep neural network. Though we also discussed the differences between neural networks and deep neural networks during unit 1. Like we can understand the concept, the basic difference between artificial neural network and deep neural network with this, that here we have more than one hidden layers. Okay, what are the major applications of deep neural networks? So here are the major, these are not only the applications, there are many more, but here I have included some domains, real-time domains, wherein we currently, this deep learning has been proved beneficial. Okay, so this deep learning has plethora of application. Almost every field, such as healthcare, finance, image recognition, has deep learning applications. So if we talk about the healthcare, with easier access to accelerated GPU, GPU, you might have heard. CPU, you know, that is central processing unit. GPU is graphical processing unit. When you have a huge amount of data, specifically image data, then you can use GPU to accelerate the uh, to accelerate the performance of your machine. So with easier access to accelerated GPU and the availability of huge amounts of data, healthcare use cases, they have been a perfect fit for applying deep learning. Using image recognition, cancer detection from MRI imaging, and X-rays has been surpassing human levels of accuracy. So that way, like not only for this disease diagnosis from uh, medical images, we also use this deep learning for drug discovery. For drug discovery, deep learning is very useful because drug discovery data sets, like data sets for drug discovery, they are very large. They are very large in size. So we use deep learning for drug discovery, and drug discovery, clinical trial matching, and genomics. They have been this are the other popular healthcare based applications. So genomic data is also very big data. So for that we use like deep learning methods. Okay, autonomous vehicles. Uh, Autonomous vehicles, like though self-driving cars is a risky field to automate, it has recently taken a turn towards becoming a reality. From recognizing a stop sign to seeing a pedestrian on the road, deep learning based models are trained and tried under simulated environments to monitor the progress. Not only that, these deep learning algorithms are also used to identify the obstacles and objects using for this autonomous vehicles. So several applications are there for autonomous vehicles too. If we talk about the e-commerce, like product recommendation, every one of you might have experienced. So product recommendation has been one of the most popular and profitable applications of deep learning. And with more personalized and accurate recommendations, customers are able to easily shop for items they are looking for and are able to view all the options that they can choose from. So deep learning algorithms have also proved beneficial in e-commerce field, and this also accelerates sales and thus benefits sellers too. Not only companies, but this benefits sellers, not only customers. The use of deep learning also benefits sellers. Okay, personal assistants. Um, in the field of deep learning, like uh, advancements are like latest advancements. They have proved uh, they have proved personal assistant is as simple as buying a device like Alexa or Google Assistant. So this deep learning, latest advancements in deep learning, they have proved benefits for this personal assistant devices too, like Alexa and Google Assistant. And these smart assistants, they use deep learning in various aspects such as personalized voice and accent recognition and personalized recommendation, text generation, and so on. So almost every real-time field that uses this deep learning algorithms today. And clearly, these are only a small portion of the vast applications to which deep learning can be applied. Okay, stock market predictions, weather predictions, etc., are also equally popular fields in which deep learning has been helpful today. Okay, so these are some of the applications for deep learning. Okay, though it is very good and have proved uh, effective for many real-time applications, challenges are also there. So some of the challenges are need of huge amount of data, explainability and fairness. So though deep learning methods, they gained immense popularity in last 1 decade or so, the idea has been around there since mid 1950s because machine learning is there since 1950s. Okay. It was a two-layer based electronic device, which was proposed in which was proposed by Frank Resumlate invented the perceptron. Perceptron was invented. So at that time, it was a two-layer based electronic device that had the ability to detect shapes and do reasoning. But advancements in this field in recent years are primarily because of the increase in computing power and high performance graphical processing units. I told you that, if you remember, during the first or second class, I told you that uh, earlier also we had this machine learning techniques, but we had not applied them because digital data was not available in real time sectors. Digital data, but today, since last 1 decade, digital data is available almost in every real life sector, and so it has been possible to apply this machine learning, deep learning techniques. So moreover, the computing power has also increased today. Earlier, if I share my experience, then when we were studying in college, we were using means of 64 MB or 128 MB RAM. I'm telling you, 120 MB megabytes. Okay, so we were not using even half gigabyte RAM when we were studying. But today you have 8 GB, 16 GB, very common. And if you want more computation power with your machines, then you can use graphical processing units. So primarily because of the increase in computing power and high performance graphical processing units, it has been possible to use this deep learning methods with huge amount of digital data. And these are coupled with the large increase in the wealth of data. These models have at their disposal for learning, as well as interest and funding from the community for continued research. So, though deep learning has taken off in the last few years, it does come with its own set of challenges, and the community is working hard to resolve the challenges with deep learning. So, the major challenges are need of data. Need of data here, if I tell you, data is not useful in if it is not of good quality. Because if you remember, I told you that garbage in, garbage out. If you feed deep learning model garbage data or noisy data, then output may not be as expected or output may not be accurate. Okay. So deep learning methods prevalent today are very data hungry, and many complex problems such as language translation do not have sophisticated data sets available. Many real time problems, they don't have sophisticated data sets available. And deep learning methods to perform neural machine translation to and from low resource languages often perform poorly, and techniques such as domain adaptation have shown promise in recent years. So, for problems such as pause estimation, it can be difficult to generate such a huge volume of data. So what we do when we have scarcity of data in any real-time domain, then we use the synthetic data. And there are different ways to generate synthetic data. Because if we have less data, we can't use deep learning models. Okay, they are not more effective if we have less amount of data. Then we can go with machine learning models. So, but if we want to generate more data, because we know that deep learning methods, they are more beneficial over machine learning techniques, because machine learning techniques, we use handcrafted features. But here with deep learning, the features are extracted automatically. So if we want to go with deep learning methods, then we need huge amount of data. And if we don't have, then we can use synthetic data. So the synthetic data, the models ends up with training on ends up training with uh, like uh, good training, in which the model ultimately needs to perform good. Okay, so there are ways to generate synthetic data if data scarcity is there. The next challenge is explainability and fairness. Even though deep learning algorithms have proven to beat human level accuracy, there is no clear way to backtrack and provide the reasoning behind each prediction that is made. The prediction is made by this deep learning model, but we don't know that on what basis model has made that prediction. So we can say that the models are black box model. What's happening inside, nobody knows, right? Even the designer of that model doesn't know that what is happening inside, because of which a particular result has been produced. Okay, so these deep learning models are black box model. So, but in many fields, like for example, in healthcare, medical professionals and patients, they are not ready to accept decision produced by such black box models. They want the interpretations of results produced by deep learning models. Okay, so this makes it like when they are not providing reasoning behind the prediction, it makes it difficult to use in applications such as finance, where there are mandates to provide the reasoning behind every loan that is approved, that why is approved, why it is rejected. So reasoning needs to provide it. So if we want to automate this manual task of loan approval using machine learning, deep learning, then reasoning has to be provided, that why loan is approved, why loan is disapproved. Okay. Another dimension that tends to be an issue is the underlying bias in the data itself. Underlying bias in the data itself, which can lead to poor performance of the model on crucial subsets of the data. Learning agents, if you remember, we talked about the learning agents in reinforcement learning. So learning agents that use a reward-based mechanism sometimes stop behaving ethically because all they require to minimize system error is to maximize the reward which they uh, receive. Okay, so in reward-based mechanism, what the algorithms need to do, all they need to do is they require to minimize to minimize system error. They are required to maximize the reward they collect. Okay, so like it is how the agent simply stopped playing the game and ended up in the infinite loop of collecting reward points. It's very difficult to figure out. So it might be accepted game scenario, wrong or unethical decisions can have a profound negative impact in the real world. So strong need exists here to allow models to learn in a balanced fashion. Okay, so like fairness, this is regarding fairness. Okay, fine. So these are some of the challenges. Like these are again not all challenges which I am discussing here, but I am simply introducing what exactly the deep learning is, how it differs from normal artificial neural network, what are the uh, applications of deep learning, and what are the challenges in deep learning. Fine. Okay. So now let us see, as per this syllabus, now let us see architectures of deep learning. Any point, any question till this point? I hope, okay, there is no question. It was, in fact, revision of the concepts which we discussed during the discussion of various topics of Unit 1. Okay. Now this is something new, deep learning and its architectures. Fine. Okay. The number of architectures and algorithms that are used in deep learning is wide and varied. Many architectures are there. This figure shows like major architectures of deep learning, and we will discuss the architectures which are shown in this figure. Among these architectures, like deep learning architectures are available since last 20 years. And among these architectures, long short-term memory, which is LSTM, and convolutional neural network known as CNN, These are the two of the oldest architectures, and also also two of the most used in various applications. Though these are the old architectures, these are mostly used today in various applications. The CNN and LSTM. Okay. Now, okay, as you can see in this figure, deep learning architectures are classified into two categories, supervised and unsupervised learning. Several popular deep learning architectures are convolutional neural networks, recurrent neural networks, long short-term memory, gated recurrent unit, self-organizing map, autoencoders, restricted Boltzmann machine, which is known as RBM. Overview. Okay, so these are like various architectures, and overview of deep belief networks and deep staking networks will also be discussed. Okay, so here you can see that supervised learning, convolutional neural network and recurrent neural networks are supervised learning architectures, and self-organizing maps and autoencoders are unsupervised learning models. Recurrent neural networks like two are very popular, long short-term memory and gated recurrent unit, which is known as GRU. Each of this is known by its abbreviation, like convolutional neural network known as CNN, recurrent neural network known as RNN, long short-term memory known as LSTM, gated recurrent unit known as GRU, right? This self-organizing maps known as SOM. Autoencoders, they are known as autoencoders only. And under autoencoders, we have restricted Boltzmann machine, which is known as RBM. So I shall discuss all this, and along with this popular architectures, I shall also discuss deep belief networks known as DBN and deep staking networks known as DSN. Okay. Okay, now before I start discussion of this architectures, remember that artificial neural network is the underlying architecture behind all these deep learning models. So that we discussed during the discussion of last unit, and this ANN, artificial neural network, is the underlying architecture for all these deep learning architectures. And based on this artificial neural network, several variations of the algorithms have been invented. Okay. So let us start with supervised deep learning, supervised deep learning models. Okay. Supervised learning refers to the problem space wherein the target to be predicted is clearly labeled within the data that is used for training. I'm repeating all these concepts. We already discussed this, that what is supervised learning. Labeled data is provided to model. Labeled data is provided to model. So that label is also known as target. It is also known as output variable, right? So target to be predicted is clearly available within the data set, which is used for training. Let us see a high level two of the most popular supervised deep learning architectures, convolutional neural network and recurrent neural networks. Okay, and some variants of recurrent neural networks too. Okay. The first is convolutional neural network. Here, I am briefly introducing you convolutional neural network because we have separate one unit on this convolutional neural network. Our next unit is on convolutional neural network. Rather, in this subject, we will mainly study convolutional neural network because it is the neural network. It is the deep neural network used for computer vision. So I'm going to discuss this in detail, but today I shall introduce it briefly that what convolutional neural network is. Okay, please be with me. Okay, now these are very important architectures of deep learning. Okay, the first is convolutional neural network. It is a multi-layer neural network that was biologically inspired by the animal visual cortex. It is biologically inspired by the animal visual cortex. The architecture is particularly useful in image processing applications. This architecture, this deep learning architecture is useful in image processing applications. Okay, who invented this architecture or neural network? Jan LeCun, who is the chief scientist of Facebook today. Okay, AI scientist. Jan LeCun invented the CNN. At the time, the architecture focus when he invented this architecture was for handwritten character recognition. Handwritten character recognition, such as postal code interpretation and so on. So initially it was invented for handwritten character recognition. As a deep network, early layers of this convolutional network recognize features such as ages in the characters, because when you write any character, ages are there. So the early layers, because there are several layers in this deep neural network. So early layers of this architecture, they are used to recognize features like ages. And later layers, they recognize the features into high level attributes of the input. So please remember, in convolutional neural network, like early recognize some of features. I'll tell you later exactly when we will discuss this again in third unit. Okay. So early layers, they recognize particular types of features, and later layers, they also uh, uh, recognize the features, and later layers recombine these features into higher level attributes of the input. Okay. Okay. Now, there are several variations of this CNN architecture, and the LeNet architecture is made up of several layers that implement feature extraction and then classification. So in this figure, which I have included here, you can see the feature extraction and then classification. I explain you, okay, it is, you can see that the earlier part, it represents the feature is used for feature extraction, and the later part, the last part, it is used for classification. So the images, when you feed image to this model, the image is divided into receptive fields that feed into convolutional layer, which then extract the features from the input image. Please remember, convolutional neural network is used for images, right? So what will be the input to convolutional network? Image. And here in this figure, you can see the image of digit 3. Because initially this convolutional neural network was designed to identify the handwritten characters. Okay, so I hope you understand this. Suppose postal code is written, and then you want machine to identify that which are the different digits in postal code. Okay, so we can use that image of handwritten characters, and we can train machine to identify this handwritten characters. Okay, so the image, you can see that image is fed to this convolutional neural network. Okay, once after convolutional layer, there is a pooling layer. Okay, what's the job of convolutional layer? What is the job of convolutional layer? The image is divided into receptive fields that feed into a convolutional layer. And what this convolutional layer does, convolutional layer extract features from the input image. Please remember, convolutional layer extract features from the input image. The next, after convolutional layer, you can see the pooling layer in this diagram. So what the pooling layer does? It reduces the dimensionality of the extracted features. It reduces the dimensionality of the extracted features through downsampling. Okay, uh, I'll explain all these terms and all these concepts again in third unit. But if you understand today, then understanding will be better when we discuss the third unit. So be with me and please understand. So pooling layer reduces the dimensionality of the extracted features through downsampling while retaining the most important informations, typically through one of the two methods available for pooling, average pooling and max pooling. Two methods are available for pooling, average pooling and max pooling. So it uses one of these two methods. Okay, now after this convolutional one and pool one, you can see another convolutional and pool, that is convolution two and pool two. Okay, so another convolution and pooling step is then performed that feeds into a fully connected multi-layer perceptron. So how many such convolution and pooling layers can be there? It depends on the complexity of problem for which you are training your model. We can have n number of such blocks: convolution, pooling, convolutional, pooling, convolutional, pooling. So we can have such n number of blocks in our architecture. Okay, here we have used only two because this is shallow CNN. This is shallow CNN where we are using such only two blocks. Okay, now the final output layer of this network is a set of nodes that identify features of the image. Okay, in this case, in case of character recognition, a node per identified number. How many classes are possible when we want to identify the digits? 10 classes, 0 to 9. 0 to 9, 10 classes are possible, right? So this is multi-class classification problem because the input image will be classified into one of the 10 classes. One of the 10 classes. If it is disease diagnosis, it is binary classification problem because whether patient is suffering from disease or not, yes or no. Okay, so it is binary classification. This is multi-class classification problem. And for this case, for character recognition, 10 classes are there because 10 digits are there, 0 to 9. Fine. So the final output layer of this convolutional neural network is a set of nodes that identify features of the image. Okay, and you train the network by using backpropagation. Here we use backpropagation when we train the CNN. The use of deep layers of processing, convolutions, pooling, and fully connected classification layer opened the door to various new applications of deep learning neural networks. And in addition to image processing, today, CNN has been successfully applied to video recognition and various tasks within natural language processing also. Okay, and here are the examples. You can see the examples I have mentioned on the slide. Image recognition, video analysis, natural language processing, this fields where we use this convolutional networks. So this is the brief introduction to CNN. Now, though I will be discussing other architectures of deep learning, in this subject, mainly you will study convolutional neural network. You will study it in deep. Okay, you will study it in detail. Fine. So this is like a brief introduction to convolutional neural network, that how it looks. Fine. Okay, the next is recurrent neural network. Okay. Recurrent neural networks, RNN is one of the foundation, it is one of the foundation network architecture from which other deep learning architectures are built. The primary difference between a typical multi-layer network and a recurrent network is that rather than completely feed-forward connections, a recurrent network might have connections that feed back into prior layers or into the same layer. Recurrent network might have connections that feed back into prior layers or into the same layer. Fine. And this feedback allows RNN to maintain memory of past inputs and model problem. So that is shown in this figure. You can see the hidden layer and you see that they are the you observe the neurons in hidden layer and you can see that recurrent network, the connections feedback into the same layer, right? So that is recurrent neural network. Fine. RNN consists of a rich set of architectures, and the key differentiator is feedback within the network, which could manifest itself from a hidden layer, the output layer, or some combination thereof. Fine. Okay. RNN can be unfolded in time and trained with standard backpropagation or by using a variant of backpropagation that is called backpropagation in time. So we can use any of them, and the applications of this recurrent neural network are speech recognition and handwriting recognition. So this is usually used for time series data and for text data. RNN are popular for speech recognition. RNN are popular for time series data, or they are popular for text data. Okay, the variant of there are two variants of RNN, LSTM and gated unit network. So let us see LSTM first, and then we will see this GNU gated unit. Okay, LSTM. LSTM was created in 1997. 1997, almost 25 years back. But it has grown in popularity in recent years as the RNN architecture for various applications. It has grown in popularity in recent years as an RNN architecture for various applications. You will find LSTMs in products that you use every day, such as LSTM is used for some applications of smartphones. LSTM is also like IBM applied LSTM in IBM Watson. IBM Watson is very popular product of IBM. So IBM applied LSTM in IBM Watson for milestone setting conversational speech recognition. This LSTM departed from typical neuron-based neural network architectures, and instead it introduced the concept of memory cell. It introduced the concept of a memory cell. The memory cell can retain its value for a short or long time. A memory cell can retain its value for a short or long time as a function of its inputs. And that's why this architecture is known as long, short-term memory, because memory cell can retain its value for a short or long time. This allows the memory cell to remember what is important and not just its last computed value. It remembers that what is important. LSTM memory cell contains 3 gates. LSTM memory cell contains 3 gates that control how information flows into or out of the cell. Okay, so associated with memory cell, there are 3 gates: the input gate, the forget gate, and the output gate. Okay, now input gate, it controls when new information can flow into the memory. Forget gate controls when an existing piece of information is forgotten, allowing the cell to remember new data. Forget gate controls when the existing piece of information is forgotten, and it allows the cell to remember new data. And finally, the output gate associated with that memory cell controls when the information that is contained in the cell is used in the output. It is used in the output from the cell. So cell also contains weights which control each gate, and the training algorithm commonly backpropagation algorithm optimizes these weights based on resulting network output error. So here we usually use backpropagation in time. I told you that variation of backpropagation is available, and the variant of backpropagation is backpropagation in time. Okay, so here with LSTM, we use backpropagation with time. So fine. So this is how the cell in LSTM works. Fine. Okay. So you can see that like left part shows memory cells and one cell is elaborated that three gates: output gate, input gate, and forget gate. Okay, recent applications of CNN and LSTM. Recent applications of CNN and LSTM produce image and video captioning systems in which an image or video is captioned in natural language. And CNN implements the image or video processing, and LSTM is trained to convert the CNN output into natural language. Right? So combination of the CNN and LSTM is used in video captioning. So this is very popular application, image and video captioning, wherein we use both these architectures of deep learning, CNN and LSTM. CNN is used to process image, LSTM is used to process that text part. Okay. Next, we have GRU networks. GRU networks. LSTM was invented, I just told you, it was invented in which year? 1997. This GRU was invented in 2014. This GRU is a simplification of LSTM. It is simplification of LSTM. This GRU model has two gates. This GRU model has two gates, and two gates are update gate and reset gate. These two gates are update gate and reset gate. Update gate indicates how much of the previous cell contents to maintain, how much contents of the previous cell should be maintained. Okay, so that is the job of update gate. And the reset gate reset gate defines how to incorporate the new input with the previous cell contents. How to incorporate the new input with the previous cell contents. So GRU can model a standard RNN simply by setting the reset gate to 1 and update gate to 0. So this way it can model a standard RNN. GRU is simpler than LSTM and it can be trained more quickly because it is simpler than LSTM and can be more efficient in its execution. So that is the advantage of GRU over LSTM, that it is simpler than LSTM and so it can be trained quickly and can be more efficient in execution. However, LSTM can be more expressive. Okay, LSTM can be more expressive and with more data with more data, LSTM can lead to better results because it is more expressive. So both have their own advantages and disadvantages. Examples of applications of GRU are natural language, text compression, handwriting recognition, speech recognition, gesture recognition, image captioning. So in all, like you know that Google is Google Translator, it is able to convert between more than 100 languages. For example, English to Gujarati or Gujarati to English. So Google supports such more than 100 languages, and all these applications, they use this RNN or RNN variants. So all these applications, like these are the real-time examples of uh, use of this deep neural networks. Fine. Okay. Now, so far we discussed all the deep learning networks, deep learning networks or deep learning models or deep learning architectures, which were supervised deep learning models. Now we will see unsupervised deep learning models. Okay. Unsupervised learning, as we all know, refers to the problem space wherein there is no target label. Data is not labeled. Okay. And this unlabeled data is used for training. So that's why the name is unsupervised. Okay. We will see three unsupervised deep learning architectures. self-organized maps, autoencoders, and restricted Boltzmann machine. So we will see three unsupervised deep learning architectures. Okay, we will also see how deep belief networks and deep staking networks will build based on underlying unsupervised architectures. So let's see them one by one. Self-organized maps. Self-organized map was invented by Dr. Kohonen in 1982, and it was popularly known as the Kohonen map because Mr. Tuvo Kohonen, Dr. Tuvo Kohonen invented this self-organized map, and that's why this map is also self-organized map is also known as Kohonen map. This self-organized map is an unsupervised neural network that creates clusters of the input data. In machine learning also, we have seen that when we feed data to unsupervised algorithm, it creates clusters based on similarity in data. Okay, so this self-organized map, they also create clusters of the input data set by reducing the dimensionality of the input. This self-organized map vary from the traditional artificial neural network in quite a few ways. And let me tell you how they differ, how it differs. The first significant variation is that weights serve as a characteristic of the node. After the inputs are normalized, a random input is first chosen. After the inputs are normalized, the random input is first chosen and random weights close to zero are initialized. Random weights close to zero are initialized to each feature of the input record. These weights now represent the input node and several combinations of these random weights represent variations of the input node. Then Euclidean distance between each of these output nodes within the input node is calculated. And the node with the least distance is declared as the most accurate representation of the input and is marked as the best matching unit or BMU. Best matching unit. Its abbreviation is BMU, best matching unit. It is marked as BMU. With this BMUs as center points, other units are similarly calculated and assigned to the cluster that is in the distance they are assigned to the clusters. And radius of points around BMU weights are updated based on proximity. So radius is shrunk. So this is how one point with like how this self-organizing map differ from artificial neural network. The second difference is in self-organizing map, no activation function is applied. No activation function is applied. And because there are no target labels to compare against, there is no concept of calculating error and backpropagation, right? So in fact, this can be considered as the normal difference between unsupervised and supervised too, right? Okay, and examples of like where this self-organizing maps can be used are they can be used for dimensionality reduction, clustering high dimensional inputs to two-dimensional output. They can be used in gradient grid result and cluster visualization. So these are the major application areas of self-organizing maps. Okay. And now, before I discuss autoencoders, I would like to know if you have any question. These are, let me tell you, these are like big topics I'm covering in brief because as you know, we are going to learn CNN throughout this subject. So see how vast CNN is. Similarly, other deep neural networks, they are also vast in concept. So if you want to learn them in detail, like you have to go through, like it's a big topic, and then you need to go through like even a minor detail of this deep neural network. But we are not learning all these deep neural networks in this subject. If your subject would have been deep learning, then you might have learned all these deep learning architectures in deep. But your subject is deep learning for computer vision. And probably after this, you may learn deep learning for natural language processing. So when you learn deep learning for natural language processing, you will learn RNN, LSTM, and GRU in detail. In this subject, you are learning deep learning for computer vision. So mainly you will learn CNN. So when we will discuss CNN in detail, you will come to know that how deep information related to deep neural network is, right? So in this unit, I am briefly introducing this architectures and making you familiar with these terms. We are not learning them in deep, okay? So if you have any question, I would like to take your question. Or I can discuss autoencoder, and then like we can stop today's discussion after discussing this autoencoders. Okay, if no question, let us discuss autoencoders. Though the history of when autoencoders were invented is hazy, the first known usage of autoencoder was found to be by LeCun in 1987. This variant of an artificial neural network is composed of three layers: input, hidden, and output layers, as shown in the figure. It is composed of three layers: input, hidden, and output layers. Okay. Input layer is encoded into the hidden layer using the, okay, it is known as autoencoders because in input layer we use encoding concept. Input layer is encoded into the hidden layer using an appropriate encoding function. So we use encoding function. The number of nodes in the hidden layer is much less than the number of nodes in input layer. You can see in this figure. Number of nodes in hidden layer is much less than the number of nodes in input layer. This hidden layer contains the compressed representation of original input. Hidden layer contains the compressed representation of original input, and the output layer is to reconstruct the input layer by using the decoder function. So we use encoder function at input layer, we use decoder function at the output layer, and hidden layer, it uses like compressed representation of the original input. So this output layer tries to reconstruct the input layer. Okay, it tries to reconstruct the input layer by using the decoder function. Okay, after this, during the training phase, what happens? During the training phase, the difference between the input and the output layer is calculated using an error function. It is calculated using an error function. Remember that I told you during the discussion of self-organizing map that we do not use error function there. And this is how it differs from the normal artificial neural network. But here, this is also unsupervised deep neural network. But here we use error function. Here we use error function. So the difference between input and output is calculated using error function, and the weights are adjusted to minimize the error. So unlike traditional unsupervised learning techniques, where there is no data to compare the output against, autoencoders learn continuously using backward propagation. So this is very different from other traditional unsupervised learning techniques. Right here, we compare output and input because output layer uses decoder function. Okay, and they are compared, and autoencoders, they learn continuously using backpropagation. For this reason, autoencoders are also called self-supervised learning algorithms. They are also called self-supervised algorithms. They are very powerful algorithms. Okay, for unlabeled data, these are very powerful algorithms used nowadays, autoencoders. In several applications, in research, people are using these autoencoders today because they have been proven very powerful, and they are self supervised algorithms, right? Applications are dimensionality reductions, data interpolation, and data compression and decompression. These are some of the applications of autoencoders, right? Okay, now we will discuss next type of deep neural network architecture. Deep architecture, like we will discuss this next time, right? So before we end, if you have any question, I would like to take your question. You can also write your question in chat box. Feel free to ask questions, right? You can ask any question related to this concepts, but because these are very high level concepts, and you may not understand them fully. So if you do not understand them fully, then you can raise your question, you can